In this video I'm going to look at data that were collected from a native oxide layer on a molybdenum foil by 3 different experiments. The first experiment is simply making use of photons to excite the electrons within the material and produce photoemission spectra. And that's what this first graph shows up here. Here we see a set of photoemission peaks, the valence band, and we can pretty much see within this that the repeat measurements are producing very similar results. The only part that might indicate a slightly different result is a growth of signal within a gap close to the Fermi edge. And this is perhaps surprising, given that this is predominantly going to be a molybdenum in a 6+ state, to see additional signal arriving here. However, most people would accept that an overlay of spectra of this nature would suggest that we've got very similar spectra that we can measure over multiple repeat experiments, and so we can use XPS to understand the chemistry of the sample. Now the next experiment involves using helium ions to irradiate the sample in between the measurements. So similar measurements that are performed in this first experiment are interleaved with the sputtering the sample by helium ions. And in this instance we can see the photoemission peaks evolve. So each one of the photoemission peaks that are associated with molybdenum change in character. The oxygen 2s is very similar in character despite the molybdenum changing, but what we see in the valence band is a significant growth of signal within an interval close to the Fermi edge. So signal is moving towards the conduction band, or shall we say the conduction band and the valence band are closing as a consequence of sputtering with the helium ions. Then the third experiment, this one involves using argon ions, the argon ions of 200 electron volts. These are monatomic argon ions, and as a consequence of performing an equivalent experiment to that of the helium problem, only this time the argon is producing quite a significant change in the chemistry of the sample. So we can see that what was originally an oxide is rapidly switching to something that has all the characteristics of a metal. The mechanism by which the chemistry is changing is potentially different between these 3 experiments. In the first instance, any chemical changes would be a consequence of the energy imparted by the photons. In this case there is no charge compensation, so pretty much the movement of electrons through the material to compensate for the photoemission is the only other perturbing factor as part of this XPS experiment. In the case of the helium, when we bombard the surface with helium ions, we are imparting energy. We have ions that are relatively low in mass, and so the damage to the surface is not supposedly that great. Therefore, what we should be seeing is the oxide as it is transformed by the interaction of the photons and the argon, which are interleaved, so they don't occur at the same time, but nevertheless there will be some interplay between the two, and as a result we see changing shapes within the spectra. And the final form, this is different yet again, because the argon, although low in energy, is typically good enough to remove material from the surface. So we might expect to see a change in the chemistry simply because the surface is being removed by these argon atoms, and ultimately we get to see the substrate, which is metallic. So using all 3 of these experiments we have a range of changes in sample chemistry and photoemission spectra, and what we would like to do is to see whether the changes that occur for these 3 different scenarios have anything in common. So what we'll do is make use of all these data to construct shapes that we believe are characteristic of the different chemistries that are being created, and then see if the trends that we expect to see within the experiments bear out as a consequence of fitting these data with the shapes that we derive from the data. Making use of the spectra from these three experiments, it's possible to calculate, as shown here, 4 different curves that represent what appears to be 4 different phases of the molybdenum. And these are calculated, these are not part of the original data sets. So it's not possible to find a specific shape that would match to this molybdenum 6+ as I've described it. The problem is that in each and every measurement there is a component that seems to derive from a metallic form of molybdenum. So no initial spectrum from the sample produces a molybdenum trioxide spectrum. So this one has to be calculated. The metal also, there's always a component of oxygen within each spectrum, so in order to assume that we've got a metallic shape, then we have to remove the oxygen from that particular spectrum. So the first and the last are actually quite easy to obtain. However, these other two require a lot of work, and it requires trial and error, removing, adding different components from the data set, and in so doing you ultimately can iterate towards this type of spectrum. I've called it 4+ and I've called them 2+. These are probably not stoichiometric forms of the molybdenum, but nevertheless this is the closest in the type of stoichiometry between the molybdenum and the oxygen. This is a 1:2 relationship, and this is a 1:1 relationship. Hence I've gone with these labels. They are not, as I say, expected to be accurate stoichiometric forms of this molybdenum, but nevertheless these are shapes that derive from the data set as a whole. So we know that these actually sit within, in vector terms, a vector space that corresponds to all of the vectors in the original data sets. Now, having derived shapes such as these, we can then attempt to make fits of these shapes to the data. So each one of these component spectra are then scaled and summed to produce a fit in a linear least squares sense to each and every spectrum. And this is an example of a spectrum from the helium sputtered sample, and the fit of these 4 components indicates that we've got the proportions of the 4+ and 2+ appearing as part of this spectrum, and the 6+ and the metal, well, there's a very small amount in this particular fit. And when we do this for each and every spectrum in the experiment where the helium was used to irradiate the sample between XPS measurements, we end up with a profile that shows us the trends that we see within the data set. And we can visually see it, but now we can quantify how these trends have occurred. I'll now illustrate some of the simple steps that can be used to calculate the profile that I showed in the previous slide. In this case, I'm going to work with the iteration form of the data set, that is to say, measurements that will just repeat measurements, no intervention by ion beams at all. So this is just evolution as a consequence of XPS. So this is the data set in its original form. You can see there were multiple measurements, carbon, molybdenum 3D, etc., all the way up to the valence band. The valence band is the set of data which I used to do the calculation of the different components and the different chemical states. So this is the one that I'm going to use to do the calculation of the depth profile. I've already prepared a file that contains the calculated curves. So these represent the different states of the molybdenum, and by selecting the valence spectra, illustrate that these are the same data that you saw in the original file. I've copied them into this particular file to do the calculation. So here we have the spectra, here we have the component spectra that we believe have chemical meaning, and by selecting the target spectra and then performing a least squares calculation, then the least squares analysis will be performed, a new file is created, and within the file there are a set of spectra that represent the original data, the least squares solution, and each of the 4 different components that are now scaled to fit the original data. We can see this if we overlay the row of spectra that represent the first iteration. And the thing to note about this calculation is that even before any iterations were performed, the sample appears to have a component from each of the 4 different varieties, including the metal. Now if I go to the bottom and select a new row, so now I have 2 rows selected, the first and the last, and I use the button on the new toolbar to display both of these rows within individual tiles. I'll then tile using 2 tiles, and we can then see what happened over the course of this experiment. That the metal and the 2+, as it's called, they pretty much have remained very similar to from the beginning to the end. But what changes is the 6+ and the 4+, both are there, but you can see by the end of the experiment that there's a lot more 4+ and a little bit less 6+. So the things that are changing within these data appear to be only the first 2 phases of this material. Now, as part of this calculation, each of the original 4 components had regions defined for the molybdenum 4P and the oxygen 2S. So the calculation of the least squares file included the regions in each of the components. The components are all scaled according to how to fit the data at each point in this experiment. So we can use the quantification parameters dialog window and the report spec property page to process each of the components using the custom report, the 4 different molybdenum components, and then all of the oxygen were given the same name. So this is going to sum together all the oxygen. So we'll see a profile that includes a separation of these molybdenum signals, but a single trace that corresponds to the oxygen. So when I press the area report, then what happens is a table is created. So for each iteration we've got a listing of the relative proportions of the molybdenum in the different phases and the oxygen, and then the percentage values, which can be converted to a profile using the Create Profile toolbar button. And then let's see if we can make this a little bit more appealing. If we adjust some of these display settings, well, we can see now that pretty much throughout the course of this experiment certain things remain constant. There's not much in the way of change of the oxygen. A little bit has diminished. The 6+ has equally diminished a little bit, but what has changed is the proportion of the 4+, and you can see that the 2+ and the metal have very much remained about the same throughout the entire experiment. So this is showing you that if you just measure by XPS, you should expect a little bit of change in your data, and it requires some other intervention, such as was the case when the sample was irradiated with helium. Then we got some significant changes.